meet again for another lesson. And before we continue, let's recall something about the delta starter circuits which we did in our last lesson. Now the circuit I gave you was one of whereby the motor was running in one direction. Now you may want to reverse direction of rotation such that your motor can go forwards as well as reverse. Now I'm going to give you a shortcut method. Maybe you're somewhere in a workshop and then you're told by your boss or somebody, you want this motor to run forward and reverse. There is a shortcut bit we can use. And of course the key thing to remember is when you want to reverse a motor, a three-phase motor, we simply, if this is your R, Y, and B, if you want to change the rotation of your motor, you simply interchange any of these two. Now the way to visualize that is that if in case you have a circle like that one there, you have a point there, number 1, another one here, number 2, another one here, number 3. Now here we can see the sequences 1, 2, 3 in a clockwise manner. But if you interchange any two, you pick on any two, you interchange them, then the sequence will be reversed. Now suppose I interchange 1 and 3. So I bring 1 here, and I bring 3 there. Now you can see the sequence is 1, 2, 3, which is now moving in an anti-clockwise direction. Remember the three phases, they are revolving in one direction. So if you want to interchange, if you want to change the direction of rotation of your magnetic field, interchange any of the two phases. So a quick way of doing it, you can fabricate something like this. In here you have one of your phases, maybe the R. Then here you have the other phase, maybe Y. And then here on its own you have your third phase, maybe the B, R, Y, B. And then you connect your motor. Now these ones go down to our motor. You can either get it to isolator or you can put it between your isolator and your starter. So this may be going to the starter circuit. And of course these three, they are all mechanically connected together like that. Now this one is a conductor. And this one is a conductor. Now you can see in that sequence, my R is the one which will be coming out here, R. Then this one here will be our Y. And this one here will be our B. Now when I flip over the switch, in this case, the switch moves into this direction here. This one comes to that connection there. And this one comes to that connection there. And this one comes to that connection there. Now the base remains constant. What I simply do, I interchange my R and Y. Now this R here will be connected to this point here and come down here as the R. And this Y here, when it's on the dot, connected to the dotted line, when it goes to the motor, it will be in that position. And this one remains as B. So in the first position, the sequence was RYB. When you flip over your switch, the sequence will be YRB. And that will change rotation of your motor. Now that is a simple way you can fabricate so that your motor you can have a forward and reverse. Now the more professional way is to use an additional contactor to do the reversing. Now when we did the DOL for the reverse, I added another contactor which I called reverse so that I'm able to rotate my motor in the forward and then the reverse direction. So for that one, the professional one, what I would like you to do is just use a contactor and redraw the circuit such that you can have a forward and reverse control. What you'll be needing is an additional start push button for the reverse, as well as another contactor to do your connections for the reverse. Now, that exercise will prove whether you have understood all the circuits you have done, the DOL plus the star and delta, and then just do that one with a contactor so that you're able to do the forward and the reverse control for that circuit. Now remember, the subject is about design. And since you have got the basics, I think that should be an easier way for you to work it out. It should be an easy way for you to work it out. It's like if you have the numbers 5, 5, I think we are all mathematicians, we did some mathematics, 5, 5. You know all about fives and you know all about counting. Now I can tell you, I want you to connect these fives, use only the 4 of them, combine them in the way you can imagine, such that you're able to get the number 56. Now, I'm sure your brain is cracking. How can I get 56 with 5 fives? Simply use your imagination, and it's a simple one to get to the answer. So for the forward and reverse direction, star delta, it's more or less a similar situation. You know how it works in one direction, how it works in the other direction. Of course, a simple way would be to duplicate the whole control system, but don't. Just have an additional contactor and see how you can reconnect the circuit to do a forward and reverse. And if you do this one here, the same way you are thinking how to solve this one here is the same technique you use when you're trying to do the star delta, forward and reverse. So I'll leave you that one too as a test to see whether you have understood the circuits we have done so far. Now, there is one more circuit I want us to do for starting the cage rotor induction motor. I think so far all the motor we have dealt with is the cage rotor induction motor. So there is one more circuit I want to do of reducing the starting voltage, and that's by the use of an auto transformer. And of course, later on we shall be seeing how we can start the wire wound rotor induction motor. Now for those 2 circuits, and also the synchronous motor starting, we'll be needing a kind of a special contactor, usually referred to as a compact starter. Now this compact starter, you buy it as a unit in the market. And this one you can use it for your auto transformer and also for the starting of the wire wound rotor or the synchronous motor starting. Now you can buy it as a 1 unit. Now here my contactor here is operating on 415 volts. So it's connected from the B phase here through its own control fuse, through the overload contact, stop push button. The starter push button need to be pressed, come through the coil, back through this control fuse, and back to the R when it is connected. Now when this contactor becomes energized, it pulls in this plunger, and then all these contacts here will make. This one is spring loaded. When there's no power, it will spring back and maintain that position. Now the plunger here is the magnetic part of it so that it can be pulled into the coil. But the connections here, where we have got our contacts, there is insulation. There is insulation so that shorting does not take place. So that when this one makes, there's no connection across the bar. So this plunger, it is magnetic, but then at the point where these contacts are, there is insulation such that there's no shorting between this one, this one, this one, this one, or when they make. So briefly, that is the construction. And then you have got the main fuses, the thermal overload, and the rest goes down. So briefly, let's see how it operates. Now when you want to operate, you simply operate your isolator. Once the isolator is closed, there is power available through the main fuses up to the top contacts of our contactor, all of them, and then through the control fuse up to the same, usually this is the auxiliary contactor number 13 and 14, up to that point there. Now when you want to start to connect power to your motor circuits, you simply press your start push button. When you press this one here, now the feed flows from the B through the isolator making, the control fuse, overload contact making, stop push button not pressed, your starter push button pressed, through the contactor coil back to the R phase. So your contactor is energized. When this one is energized, all these contacts will move to the left. So through the contactors, this contact here, and this one here, power is available to the motor. Now when this one makes here, it provides a parallel path between the start push button and this contact here. Now these ones become a hold-on contact when we release our start push button. Remember, we saw that this one is spring-loaded. When you press, the sequence starts, you can release it. And when you release it, our path for holding in our control contactor coil will be through this contact here, which is our hold-on contact. And then, when you want to stop, you simply press your stop button. Now the overload, it can be actuated when there is an overload. And remember, when I showed you in the overload, there was that red push button. When you press that one mechanically disengages this overload contact here. That's why you are also able to disconnect power to your contactor coil, and then your power to your motor stops. So this is a component you buy on its own, and you can use it for the other two circuits that we are going to discuss. Again, briefly, when you close your isolator, the power is available up to the top contacts of our contactor coil and up to the starter button at this point here. Then when you want to start, you simply press the start push button, and once you press it, the feed is available from B through control coil, through control fuse, overload contact making, stop push button making, starter push button now making. Our contactor coil is energized, and once it is energized, these contacts will make, and then power is connected to our motor circuits. And then when this contact also makes, like the other ones when they are making, it provides a hold-on contact, an alternative path for the current when we release our start push button, so that the power to the motor circuits remains continuous. And when you want to stop, you simply by interrupting the power supply to our contactor coil. So let's have a look at the auto transformer circuit. Now, for the auto transformer, I think we all know its operation. The primary and the secondary, they are all in one winding, the auto transformer. And in this case, these are three-phase auto transformer. So for the L1, there is that winding there, and they are all connected at this point here. For the L2, that winding, the one in the middle, connected there, and L3, this one here, connected at that point there. And then we have got our motor here, and these are the motor terminals, and I've connected them in delta. Remember, we said that the windings for these ones, they are connected in the BS manner, something like that. So when we just put a connection down like that one, the connections for the motor will be in delta connection. So now from our compactor starter, which is this one here, the power down here to the motor circuits, these contacts here, these wire connections here will be these ones here. Remember, the overload bit is taken by the compactor starter. So the power is available here, and then the whole of the voltage is dropped across the winding. Now, the low voltage, we have got this auto transformer. There are sliders, and depending on the motor, well, this starting voltage will depend on the voltage ratio of the auto transformer. So where this sliding is, now these three sliders, sliding contacts on the auto transformers, they are mechanically connected, so they move together up or down. So when they are in the downward position, we are simply getting the voltage to the motor, which is on the lower end. That will be the voltage going to our motor. So if this one is pushed a little bit lower, the voltage will be less. And then when you want to increase your voltage, you simply raise this one, pull it up until when you reach the run position, whereby now the entire voltage will be connected to the motor. L1 will be going straight to the motor bypassing the transformer once it has started. Now the key thing to remember is that these sliding contacts here, they are mechanically locked such that you are not able just to push them from the starting position to the run position. You move in stages. In industry, there is a mechanism of making sure that you don't simply slide it from start to the run position. So they go in stages. Remember, at a lower voltage, when you start, the current will flow in. The motor, there's a back EMF developed. The current will decrease, the one which is being drawn into the motor. So that difference in the current is the one which is used to control, to interlock the moving of your slider. This slider can either be pushed up or it may be rotary, depending on the design of your auto transformer. So when you're starting your motor, you start at a lower voltage. Now this voltage, depending on the size of your motor or the loading of your motor, you decide on which voltage to start. The tappings have got some values. They are all rated. And then you start with the lowest, and then you go on increasing as the motor gains speed. You go on increasing until you reach the run position, whereby the entire voltage now is connected to your motor. So here we overcome the initial inrush of current into the motor. We don't interfere with the power system to interfere with our neighbors. So that, I think, gives us the four methods we talked about starting of large motors. Remember, this is a large motor, it cannot be connected direct online. We started with, you can have series resistance connected to the stator windings. You could have an inductor connected with the stator windings, or you can do the star delta. You start in star, you change over to the delta, and then you have got the auto transformer to give us a lower starting voltage, and to increase it, and the motor gets the full voltage to run. Again, the motor here is a cage rotor motor. The rotor has got the copper or aluminum bars. There is no winding on the rotor. And I think with that, we have learned methods of how to start cage rotor motors. So next, we are going to have a look at if the rotor has got a winding, how do you start it? And that is the next topic. In the wire wound rotor induction motor, now our rotor has got windings. So these are stator windings. These are the rotor windings. Now, the problem with wound rotors is how to interconnect these windings externally, since they have to come out externally for connections. Now, this is done via slip rings, and then we have got brushes, and then the brushes you can connect to whatever other circuitry you want. In our case, we want to connect starting resistors in series with our windings. Remember, when there's a winding here, the winding here, there are two windings. The transformer action comes also into play. And one of the reasons why these wound rotor motors are not very common is this slip ring arrangement here. It causes a lot of problems. Now the slip rings are mounted on the same axle as the rotor windings, but of course they're insulated from the windings. And then we simply, there's a facility to connect the windings onto some external circuits. And then here we have got some resistors which we connect in series with the windings. And we have got a stopper here for the off position. And then when you want to run, you move it in an anti-clockwise manner. Of course, again, as you move anti-clockwise manner, the stages are interlocked. You cannot just slide it on to the on straight. Just like we saw for the auto transformer, there is interlocking so that you don't go from the start to the on position. So this will be our starting point. And then you've got your handle to rotate these three arms, which are electrically and mechanically connected together. And in most cases, they are spring-loaded, such that when the motor runs, you switch it off, this should spring back to the off position, so that the next time, in case you connect the motor, it does not find a short circuit, there can be problems. So when you want to start, you simply, from a compact starter, you switch it on, we're able to get our feed to our stator windings. And those ones will induce an EMF here. And then the moment you start turning in your arm here, this arm will move to the beginning of this resistance here, this one to this one here, this one to this one here. So that these windings are connected in series with resistors. In our circuit analysis, there is a question of the currents and the torque that can be generated. We want a bigger torque starting, these resistance values must be higher, but more of that in our circuit analysis. So in the starting position, the whole of the resistor is connected in series with our rotor windings. Then you simply, as the motor gains speed, you simply turn this arm clockwise. Usually in a handle, you turn it clockwise, and then as you turn it clockwise, you simply be reducing the amount of resistance which will be in series with your rotor windings until you reach this point here, which is on, whereby this resistor will be completely out of our rotor windings. The rotor windings will be shorted, and then this one comes back the same arrangements like we had for the cage rotor. The windings are shorted. Now, when the motor is running, we'll have problems with our bushes here. The bushes wearing out, it's running at full speed. Question of bushes wearing out, there is some resistance, loss of power, and there is also mechanical wear and tear. Now that one is overcome in very large motors, whereby we have got arrangements. Now you can see when the resistances are completely eliminated, the shorting will be through the arms. The shorting of these windings here will be through the arms, since they are electrically connected. So it simply be like shorting these ones here. Now in very large motors, to overcome the problem of the split slip rings, what happens is, when you attain full speed, there is a mechanism that will short the slip rings together, so that now we eliminate the question of the friction, and then the brushes are lifted off the slip rings. So the wear and tear and the loss at the point of contact, the electrical losses at the point of contact, the wear and tear is simply done away with. But that is for the large motors. You short your slip rings, which these arms were doing, and then once they are shorted, there is no need for the brushes to be attached to the slip rings. There is a mechanism for lifting them up. And of course, once you stop your motor, then the slip rings must come back, the shorting must be removed, and these arms must move back to the off position, ready for the next operation. And I think that much is all there is to tell about the wound rotor induction motor. Different torques, different resistances, the currents involved, circuit analysis. The circuit is something like that. And this is one reason why these wound rotor motors are not very favored in industry. Unlike the cage rotor, very robust, no problems with slip rings. But with this ones here, that problem comes in. So we have seen how we can start the cage rotor, and we have seen how we can start the wound rotor induction motor. The theory is more of it in the circuit analysis. And I think that finishes on the motors. So in our next lesson, we shall briefly talk about the starting of our synchronous motor. As you know, the synchronous motor is not self-starting, so we shall find out how do you start a synchronous motor. And of course, once we finish the synchronous motor theory, we shall move on to the practicals. And the practicals will be for the first 3 circuits that we did. And that completes the motors. Induction motors. Next lesson, synchronous motors.